In the previous segment, we talked about how any dynamical system can be thought of as a combination of springs, masses and dampers, and then we saw in fact various degrees of complexities in increasing order. Okay. And then we saw in what way we will move from the simplest case of spring mass system to the acoustic system. And in doing that, if you remember the previous segment, I also had started by referring to two ways of thinking about such system. One is about frequency domain and one is the time domain analysis. Okay. Now, in this context of the complexities which we discussed, what exactly do they mean? You remember when we said that the natural frequency or natural vibration of a spring mass system. So that in that case you had only one thing which was the you were not doing anything more than you are just displacing and then leaving it. Okay. So under such conditions what happens is the system, to describe the system, easier way to describe the system is in terms of the natural frequency with which the system will vibrate. That means you pull it, leave it, and the system will just oscillate, right? So just let me say I'm not doing anything now in quantitative way. We will come to that in a moment, but I pull it and left it, and then it will oscillate. All of us have the experience of seeing such things. Okay. If we just neglect the all damping factors of air resistance and all, it will keep on oscillating at a certain frequency. Okay. And that frequency is called the natural frequency because the vibration is natural and no external load is there. So now for this kind of a system, when you talk about that frequency, everything you have mentioned basically, okay, in a way. But then when you go to the next level of complexity where you applied the force function as a sinusoid, okay, a sinusoidal forcing function, then again if you mention about the frequency or the time period at which you are oscillating the system, more or less things are set. Okay. We will see why that is so quantitatively later, but more or less that becomes fixed once you talk about the frequency with which you are oscillating. Okay. Now, in these two cases, when I am saying that as soon as you fix up the frequency, okay, in a way you have completely described the system. So that way of thinking is called the frequency analysis. We are not even thinking about how the system, once you leave it, this one will keep on oscillating with respect to time, because it's not interesting, right? Because see, you leave it and it will keep on oscillating like that forever, and no changes will happen in that movement or the motion, and that's why it is dull to talk about that. Yeah, the same thing happens forever. So you just tell that its natural frequency is say 10 hertz, and that's it. So if you tell this, everything is, you have told about this. Similarly, this also, if you keep on oscillating it at say 15 hertz, and the mass will keep on oscillating at say 15 hertz frequency, and nothing interesting happens thereafter. So why to talk even about time in that sense? So only thing which is now interesting is this 15 hertz at which you are oscillating it. Okay. And similarly, once you go to the other complex conditions, for example, when f became periodic, like that. Then what? So then what to talk about? Means now is the time interesting or the frequency? So in this case, see, up to certain time is interesting, because say up to this level one cycle hasn't repeated yet, but after that this cycle keeps on repeating. Then here this time over which things were changing without repetition was really interesting, but after that again you can say that okay, this thing happens again and again and again, so no interesting thing happens. So here what you can talk about is either you express or analyze the system over this complete period, okay, that everything happens during that period of time, or there is a way to talk about also frequencies that we will actually, I am coming to that in this segment, that in fact instead of talking about this period of time, you can also talk in terms of just frequencies. Now it's not a single frequency, but there are certain frequencies you will be talking about, okay. And similarly, once you go to the next complex level where it is just a periodic signal, there also you can talk about a lot of frequencies, because now the whole of the time is interesting. It never repeats, you know, the force you are applying is never repeated, it's always changing. So that means things are happening always, some changes are happening. But now if you see from this to this, that the importance of time is increasing in a way, and the importance of frequency is decreasing. And if you go from this to this, the importance of frequency is more and more increasing rather than the importance of time. So but all these systems or all these complexities can be analyzed or talked about in terms of frequency or in terms of time. So that is what we are going to see in this segment. And as I mentioned in the beginning, in fact I started the thing with that, the whole thing, subject of vibration and acoustic always is discussed in these two phenomena, or these two perspectives, I would say, okay. One is to look in frequency, one is to look in terms of time, the evolution of the system over time, or you talk in terms of okay, if I apply such a sinusoidal like this, okay, if I apply a 15 hertz sinusoid, then what happens? If I apply a say 150 hertz sinusoid, then what happens? So such questions are answered in frequency domain. And what happens at say 37th minute of time? So such kind of questions are answered in the time domain analysis. So that is what is another major perspectives, two perspectives through which we should see the subject, okay. Now having said that, let's get into the quantitative aspects of all these things which we till now just discussed qualitatively, okay. So we will start with the say simplest spring mass system, as I had told you earlier, that there is a spring and there is a mass m, stiffness k, and suppose from the equilibrium condition you are measuring x to be in this direction, okay, and then you write the differential equation which tells you that see the acceleration d square x over dt square of this mass will be equal to the total force that comes onto this mass, right. Now, what is the amount of force that will come if you have pulled it by a distance x? So, a negative force in the upward direction, a negative of say minus k times x is coming onto the system, right. So, that is the equation which governs, this is the simplest of the equation which you can think of, which governs this thing. And here you can in fact write this as over dt square, I will write it as k over m, x is 0, and just note that this stiffness can never be negative, this m can never be negative, because both are physical quantities, they have to be again now positive, mass and stiffness. So, to tell this fact that this coefficient of x ought to be positive always, I can in fact write this as say d square x over dt square plus some constant square times x equal to 0. So, now that becomes our differential equation for this spring mass system, right. And then all of you, I know that you are completely aware of this, I am just repeating this so that we will be on the same page. Okay. Now, if I tell you that again you see here nowhere we are talking about any external influence in this. So, that is important to observe, notice, and to tell yourself that yes, this is why it is called the natural vibration. See this the only thing which contains any parameter related to the system is this, the coefficient of x, and that is it. So, that contains both k and m, and those are the only physical parameters which the system has got, and in terms of that the differential equation is set. And now, what do you mean by solving this differential equation? It means that you are let me be explicit here to tell that okay, these are functions of time, isn't it? This x is a function of time, and that is what you are actually trying to evaluate. When you say that I want to solve this differential equation, so you mean that you want to solve for this function xt. Now, how do you solve it? Obvious, you will tell me that you will assume sinusoidal functions, but we will not do that. We will just do even more basic to that. We will not assume that you know sines and cosines, and we will talk something more, even more fundamental way of solving a differential equation, which in fact is in a way the best way to start thinking about any differential equation, and that is by guessing. Let's try to guess what its equation, the solution will be. And this guesswork, when we do, we will not guess in any arbitrary way, we will guess in a very systematic way. And why I am saying this is, this way of guessing or systematic guessing will be applicable even in more complex problems, which I will give you as assignment now after we solve this. Okay, let us see this, how to guess now. Okay, let us guess. See, xt we are trying to figure out, and there is no reason why we will think that s will not be continuous in this case, isn't it? It's a physical system, you have pulled it and left it, so it will just move like that, and there is no reason why should it be discontinuous. So it will be continuous, and it will be a good natured function, isn't it? It will not have any peculiarities like non-differentiable things, because things are smooth, isn't it? The feeling also tells you that. Now if that is so, then that means this xt which you are going to now guess, that also should be having these good nature behaviors. So that means we can assume it to be actually polynomial in time, because it's a function of time. So we can actually assume it to be a polynomial in time, say like this. How would I say x t, I would, sorry, suppose I assume it as say a naught plus a1 t plus a2 t square plus a3 t cubed and so on. Okay, that's a reasonable assumption, which I call a systematic assumption, that it's a continuous and good natured function of time. Okay. Now the thing is, you just have to now replace this or substitute this in this equation and try to figure out these constants. So that's what we are going to do. Now having said that, let me just what do I do? Do I have these terms? Yeah. So if you substitute, in fact you will get these terms. I'll write them. Okay, this d square x over dt square will become, okay, 2a2 plus 6a3t plus 12a4t squared, etc. And your omega squared x will become something like omega squared a naught plus omega squared a1 t plus omega squared a2 t squared plus like that. Okay, so these are the two things which just I have substituted here, nothing else. Okay. Now if that is so, then the differential equation says that this plus this is 0. So that means, and then for all time to come, that has to be satisfied. Okay. Now if I sum them up, okay, so that whole thing has to be 0. So that means term by term every coefficient has to be 0. Now if you do that, what you will achieve is, you will get this a2, okay, to be equal to omega squared, sorry, negative of omega squared a naught over 2. Similarly a3 you will get as negative of omega squared a1 over 6. Then a4 negative omega squared a2 over 12, a5 okay, or just a minute, a4 here, see you got a2 here, so a2 is in terms of a naught again, so you can write this as in terms of omega to the 4 a naught over 24, and like that, and then you can keep on calculating the next terms. Okay. Okay, now if you substitute these things here, okay, now just note that from a2 we have sorry, I'll use a different color, say A naught and A1. So these are the two things which are going to come in all the other terms, and in terms of these two parameters all other terms can be written. And if you do that, you will actually get to a condition like this. So your x, your x will be like this, say A naught times 1 minus omega square t square over 2 plus omega 4 t4 over 24 minus omega 6th t6 over 720 etc. plus A1 times or A1 over omega, I will write, then 1 or omega t, here omega t minus omega cubed t cubed over 6th plus omega 5th t 5th over 120 minus omega 7th t7 over 5040 etc. Okay, so that is how you will get it. Okay, now we just note that we didn't assume that anything about sines or cosines or anything like that. We just assumed simple thing that there is no reason for xt to be a weird function, it should be a good natured function, and any good natured function can be approximated as a polynomial, and that polynomial we substituted and we saw that they are coming like this. Now in fact these are the expressions, okay, this is one and this is one. Now these we call, we have given some names because you know in physics these kind of expressions people saw that they came up again and again and again in many places. So why to use such long expressions? So just they thought that why not just give some short names to them, and they were given, and that is what you know them as, you know. So this is sine of omega t, and this one is, you know, cos of omega t. Am I correct in that? Because if I put t equal to 0, so it becomes 0. Yeah, so that's the sine and that's the cos, isn't it? Omega 2 is 0, so it will become 1. Fine. So that is the cos, and that is how we know them as cos and sine functions. Okay. In fact, all of you are quite familiar with this notion of, say this is theta, and say I'll call this what, the base, the height, or I think it was called p, and this h hypotenuse, right? And you know sine, so this theta is nothing but say omega t in terms of this, if I want to write. So you always have got this notion of sine theta and cosine theta and tan theta in terms of these ratios of the lengths. But then what is this? The idea is, the point is, this is what the actual or the algebraic meaning of the sine function. This is much more powerful than this way of thinking, though that's also useful. That's the geometric meaning or the trigonometric meaning of the sine function, but this is the algebraic meaning. Why am I saying that it's more powerful? It's more powerful because now you do not have any restriction on um, on putting these argument to be complex numbers. Sorry. Okay. Now in this case you have no clue whatsoever. If I tell you that, okay, what if theta is equal to 3 plus 2i, okay, now so that you are stuck, you can't do anything now. But here you don't have to think about anything, you just substitute in place of omega t 2 plus 3i, and then whatever value you get, so that's the sine of 2 plus 3i. Okay. In fact, you can check that on your calculator. Try to calculate sine of 2 plus 3i. It will give you an error most probably, and but then you go and use say MATLAB to, and then there you try to evaluate sine of 2 plus 3i. You will get it, because that's the more general way of evaluating which MATLAB uses to evaluate sine, and you will be able to evaluate the complex valued sine and cosines and tans. And then that's the basic idea of, why I just went into this is I wanted to show that this, what did I do? I think I undid something, whatever. Yeah, so solving a differential equation is nothing but a guesswork, and by that same method I just wanted you to solve this one more equation which we will come across later. So that's this, say d square 1 over x dy over dx plus 1 minus 1 over x square y equal to 0. Now suppose this you have somewhere you have got an equation like this, and you want to solve for y as a function of x, okay, sorry, like that. So y explicitly, if I want to write, so it should be like this, isn't it? That x could be time, fine. Now this, if you try to solve, which you the answer which you will get will be called a Bezel's function, and which will be okay. In fact, let me write that, so you will get something like, you can try it out, that a1 times x minus x cubed by 2 times 4 plus x fifth by 2 times 4 times 4 times 6 minus x seventh times 2 times 4 times 6 times 4 times 6 times, sorry, something like that. Okay, now this is what you will get, and again we will see later that this expression will come up again and again and again. So they thought that why to use this big expression, and just an abbreviation for that was say j1 of x. Okay, so it's called the Bezel function. We will come to them later with much. There are many more properties, and then why this one, from where it has come, and what are the properties of such functions. And then one more important point which I want to point out here, that here in the previous case you got two parts, cos and sine, and here I have mentioned only one part, the Bezel's function. So there is slight complexity in this, you should think about, so that's also your in a way homework, that this x, when it is sitting in the denominator, will make things a little bit complex when x becomes 0. So that is why one of the solution, which will be termed as the Neumann solution, so that part is a bit trickier to get from this thing. Okay. So I just wanted to make the point that okay, Bezel's functions are nothing but some special symbols which exactly like sines and cosines, which we have given to those expressions. So Bezel's functions and Neumann functions, so they are also some symbols which we have attached to some big expressions like that, infinite series of summations. Now, so coming back to this, you should now think about why you always told that, you know, when there is a differential equation of second order, you require two initial conditions. So that is where these two initial conditions are lying. Without knowing a0 and a1, you cannot actually now go ahead evaluating xt. So I should write it here t, right. So explicitly, so x is a function of time. You can evaluate only when you know a0 and a1 over omega. But then this is the algebraic way of dealing with it, but what about their physical meaning? What about this a0 and what about this a1, and what they have to do with this pulling and hitting business? Because as we told in the previous segment, that this first natural vibration has nothing to do with force, but it has to do only with pulling, pushing or hitting. Now so that means only if these things are happening or their combinations, so that means these constants, what we saw here finally, must be having something to do with those pulling, pushing or hitting. Now what is that thing? How are they related? So that we will be discussing in the next segment. See you in the next segment.